and today's lecture is going to be on min cut, which is once again one of my favorite algorithms. So this is lecture 10, I believe. Min cut. And the date is the 17th. Okay, so maybe before jumping into min cut, I would like to talk about something different that would turn out to be useful, and that's related to your homework. One of the questions in your previous homework. So let TH be the complete binary tree. Complete binary tree. Of height h. Complete binary tree means that it has 2 to the h children, right? So this would be T2, right? And we're going to play the coloring game, right? So every edge is going to be colored blue with probability half. And otherwise it would be red with probability half independently. And let's assume that the question is, let pH be the probability of a red part from the root to a leaf. Red part to exist from the root to a leaf. Okay, so I'm interested in this probability, right? And this case is somewhat different. You know, it's similar to what you had to do, but it's somewhat in a different regime because I want to know what the probability is. So let's start doing some easy cases. P0 is 1, right? Tree of height 1. The probability is, of course, 1 that there are no edges. So, of course, the root is its own leaf. So there is always a path. It's an empty path, but empty is a valid path. P1, well, we are dealing here with the tree of height 1. Right, so the root has 2 children, and the only bad case is if both edges are blue. The probability for that is a quarter, right? Probability of the left edge being blue is half. Probability of the right edge being blue is half. They're independent, so probability of both is a quarter. So P1 is 3/4, right? Because it's the complement. It's 1 minus 3/4. Okay. So, and now we can write down the general formula, right? So how do we do that? So let's look on the roots, right? And it's going to have, let me use a different color because colors are important. We have the roots. The root have 2 children. This is TH minus 1. This is TH minus 1. And now I would like to know what is pH, right? So the idea is that let's look on the probability of success on the left side. The probability of success on the left side is, well, this edge has to be blue. That's probability half. And then there should exist a path in this subtree from this node all the way to a leaf. This is by recursion pH minus 1, right? So the probability of having a left path on the left side is pH minus 1 divided by 2, right? Okay. So this is the probability that I succeeded on the left side. And since there is no success like failure, the probability that they fail on the left side is this, right? This is the probability I failed on the left side. This is also the same probability that I failed on the right side. And of course, the two events are independent, right? So for me to not have a path from the root, a red path to the leaf, I have to fail on both sides. Those are two independent events, so I multiply them, right? So this is this. So this is the probability of failure, but we are interested in the success. So pH is just 1 minus this, right? And now you can do some arithmetic, so let's do it, because there is no reason to fear. 2 pH minus 1 minus pH. Oh, it's not 2. It's pH minus 1, right? Minus pH minus 1 squared over 4. Okay, the one cancels out, so this is just pH. Okay. So now we got the exact probability of success. Any questions on this? And of course, if yeah, go ahead.
Some student just mentioned this is the homework problem.
Yes, this is very similar to the homework problem. The homework problem was somewhat different because the question was to ask what degree do you need to do such that you guarantee that probability at least half, right? Now, if you look on this probability, pH, if you look on pH, pH is going to decrease as you increase H. In particular, let me write the lemma because that would be kind of important. So lemma, pH is larger, this is H not N, 1 plus H plus 1. And pH is smaller, is okay. So one can prove that pH is roughly 1 over H. And the proof is in the class notes. This is a tedious inductive proof. The upper bound is tedious, the upper bound is even more tedious. But you can accept it on faith. What you were asking the homework was to decide what degree do you need such that this probability P of H would be larger than half for all H, right? And I didn't do the exact calculation, but if the probability for red is P, then the answer should be, the degree should be something like, I don't know, 3 over P or something like that. Maybe 4 over P, some constant over P. It's not too difficult to see, essentially arguing as we did here, essentially. Okay, anyway, this is how it's related to the homework question. And of course, the homework question was not, I gave you the homework question because we were going to talk about this, right? Okay, other questions about this? Okay, so did they mention Galton-Watson processes? Galton-Watson in the first lecture? Yes, no? Did I ever mention it? Do you remember? Okay, so if nobody is claiming that I mentioned it, I assume I didn't. Just want to make sure because it's kind of one of those long, complicated. Thank you. I didn't follow the chat. Let me now try and follow the chat. My bad. Okay, so the Galton-Watson process. This is one of the stories about the British Empire that show you why there were a bunch of well, you decide what the value of is. So Galton in the mid-19th century asked, I think it was Galton that asked it. Let me verify. Oops. So the worry was that, oops, what is going on? Oh, here we go, finally. Okay. Yeah, okay. So Galton, Francis Galton asked in the middle of the 19th century why names of blue blood families in the UK were disappearing, right? So the basic idea is that males are carry the family name, and then so the Galton-Watson process starts with a single node, which is the ancestor that begins the family name, and then they have children. Okay, now what happened is that children, the male children carry their family name. Females, when they marry, they change their name to the family they marry. So as such, when we speak here about children, I'm really speaking about here only about male children. And also we're asking only about children that survive till adulthood, right? So the idea is that this node has a random variable x, which is the number of children. Okay. And so we have the number of children. So each one of them has, this has several children. Now, for every child that survives to adulthood, the process continues, right? They're going to have children. Again, the number of children they have is a random variable with the same distribution. Unfortunately, I drew it is for, let's say, 2, maybe 1, right? You have to, of course, remember that at the period, families had a huge number of children, but large fraction of them died, right? So we are not used to this idea that most children die, but it definitely was a situation well into the 20th century, I think, that the probability of survival was definitely to adulthood was below 50%. And now, so this tree continue, and essentially the question is, if I give you X and I give you its distribution, this is the distribution. Is there a condition that tells me whether or not, so X, again, X can be 0, 1, 2, and so on. And the question is, what's the probability that, let's call the root V. V generates infinite tree. Infinite. Okay. So what information I give you on the distribution? So what Galton looked on was the expected number of children, right? And what one can show is the following thing. If the expected number of children, right? So to remind you, every node in this tree has the same distribution of the number of children. If the expectation is larger than 1, then this probability, let's call it probability of infinite tree, this probability is strictly larger than 0. If the expectation is smaller than 1, then this probability is infinite. It's 0. Okay, so which is kind of intuitively clear, right? Now, of course, the question is what happens if the expectation is exactly 1? Anybody wants to make a guess? What happens then? If the expectation is exactly 1, what's the probability of having an infinite tree? Just make a guess. Sorry, I couldn't really hear you. Can you repeat? Can you please repeat?
It's also 0.
It's also 0. And the intuitive way to see it is just to realize that if the expectation is 1, it's a very fragile situation, right? So it's kind of unstable, so it has to be 0. But that's, of course, not a proof. This is just for, okay. So Galton asked the question, Watson answered. Watson essentially gave this answer that I just told you. And this is called Galton-Watson process. And in fact, it's very important because people use it all over the place in analyzing, natural biological processes of growth. It's used in natural language processing. And if you think about it, what the coloring game that I told you about is yet another Galton-Watson process, right? Because here the distribution for the number of children is either 0, 1, or 2, where the probability for 0 and 2 children is about a quarter, right? And the probability for 1 child is half, right? So the expected number of children is 1, and this is indeed the case that the probability of infinite tree is 0, and that's in fact what the lemma shows, right? The lemma tells you that this probability goes to 0 with h. It doesn't go to 0 too quickly, but it goes to 0. Okay, and there is a chance. There is a chance later on in the course that we will revisit those Galton-Watson processes in analyzing a constructive algorithm for something called the Lovász-Loka lemma. I hope to do it this time. And then we'll visit again. But in any case, it's nice to know about it. By the way, just as a random tidbit, this family name distribution is very interesting, right? So it turns out that if you look on cultures where family names exist for a very long time, like Korea, for example, then you have very few last names, right? A lot of Koreans have last name Park or Lee. And that kind of follows from this, you can kind of realize it from this process somehow, that you get this domination of a few names. On the other hand, cultures that have much shorter history of last names usually have a huge number of last names. And of course, some of it, of course, now disappears, right? Because, for example, in Israel nowadays, when you get married, you can choose either to change your name to the husband name, or both husband and wife are allowed to create a new name. And that's very common in Israel. So usually if you see a last name from Israel with a dash, it usually means that they merged their last names. It's not the case in my name, but for many other cases it is true. This is just a general tidbit. Okay, so this is all I want to tell you about Galton-Watson. Questions about this before I go and jump into the min-cut stuff?
I don't see why when it's the expectation is 1, it's not an infinite tree, because I mean you said it was a sensitive or fragile process, but
I didn't prove any of these theorems, so you cannot see it. But maybe the best way to think about it is that think about looking on the tree layer by layer, right? So think about exposing the tree, right? You look on the tree of depth 10, depth 20, depth 30, and so on, right? And the intuition is that if you look on this finite tree, you can look on the distribution for this finite tree, right? On the distribution of number of children per node. And essentially what happened is that in some of those finite tree, it would behave like it's larger than 1. In some of them, it would behave like it's smaller than 1. It would essentially,
I see.
It will essentially
Averages out, or
it will
someone doesn't have
alternate. It
Right.
would alternate, and at some point it would alternate to the point where essentially it would have to be finite. This is kind of this is extremely hand wavy. So
Right.
hopefully you get some wind to your Zoom screen. But
Yes, that helps. Thanks.
yeah. Yeah, in fact, I never looked on the proof of this thing. I don't think it's very hard. It might be worth exploring. If it's nice, I might present it or something. Okay, other questions? Okay, so min-cut. Okay, so I give you a graph. And I should say that here we're dealing with the simplest case. So the graph is going to have n vertices and m edges. And if I pick a set of vertices S, then there's going to be a complement set of vertices. Okay, so. Right. And we're going to use this notation as this is going to be all the edges in the graph, UV in the edges of the graph, such that U is in S and V is in not S. Okay. So those are all the edges that essentially have one point in S and then another point outside S, right? So this is called the cut. Okay. And of course, we are interested, min-cut ask for compute S that realizes. Okay, so realizes what? This is the, maybe let's go back to black. Minimum over, let's call it T just to keep things simple. T is a subset of the vertices. We don't want empty, we don't want empty set. We don't want all of them, right? So non-trivial subsets. And we look on all the, okay. So we are looking for the cut that have the fewest edges across it, right? Now, people really care about this problem in practice because think about some, you want to run some graph algorithm, or in fact, any algorithm on a graph, you want to break it up, right? You want to break it up into sub-problem because you want to apply a recursive algorithm. Maybe you want to run some simulation. but you want to break it as cleanly as possible, right? Now, cutting the graph completely cleanly, you cannot, because the graph is connected, right? By the way, I didn't say it, but I'm assuming that G is a connected graph. If it's not connected, this question is not interesting. Okay, so somehow what you want to do is you want to find the best way to break up the graph, and the mean cut is a good candidate, right? It's the natural way to just take the minimum number of edges that if you remove them, you break the graph, and then you recurse on one side, recurse on the other. So it's a natural question. And a priori, it's not even clear why computing how to compute the minimum cut. It's not even clear, and the reason why it's not clear, because maximum cut, right? So you want to find the cut that maximizes the number of edges. Then if you want to maximize the cut, max cut is NP hard or NP complete, depending on the version you look at. Let's call it NP hard. Okay, now as far as the question on the chat, I'm now here assuming that the edges do not have weights. Of course, the general version of the problem is the edges have weights, and you're trying to minimize the total weight of the edges getting across the cut. It turns out that the weighted version is not much harder than the unweighted version. But for our purposes, we're just going to do the unweighted because it makes life so much easier. Okay. So it's not even clear how to do it, how to compute the minimum cut. Now, if you know flow, network flow, which I'm not going to assume that you know, if you know network flow, it's not hard to show that if you run network flow n times, or n minus 1, and let's say n times, then you can solve mean cut. Okay, but that's pretty expensive, and it's also complicated because network flow, just teaching you network flow, in fact, presenting network flow and proving a polynomial time algorithm for network flow, this is essentially 2 lectures, right? So, and I'm essentially going to present an algorithm for mean cut, which is extremely simple. Okay, so we're going to use a basic operation, which is going to be edge contraction. Okay. By the way, I should mention this algorithm was discovered by David Karger when he was a PhD student. He's faculty in MIT. It's a beautiful algorithm. Okay, so what is edge contraction? Let me draw my favorite graph. A house in the prairie. I'm not going to draw the cornfields, they're boring. And let's call this UV. Okay, this is G. Okay. Okay, contraction is essentially you take an edge in the graph and you contract it. You essentially identify, so in this case, this is going to be this edge. Okay, I tried to change the color, not successfully. Let's try again. You take this edge and you contract it, right? So if I do that, the new graph, let's draw it. It's going to be, right. There's going to be a new vertex, which I'm going to label by the 2 vertices that it corresponded to, right? And there's going to be, the door became now a triangle. And there's also the old edge, the old blue edge is becoming a self loop, right? It's going from itself, right? Okay, so this is the contraction operation. And you can do edge contraction in linear time. Edge contraction can be done in O of n time. Okay, so I have to tell you a little bit about it. I'm not going to go into all the low-level details because in this case, they become mind-boggling, tedious, and boring. But let's have a go at it. So the graph is given as a Johnson C list, right? Graph is represented right. So a Johnson C list means that every vertex has the list of all its neighbors. And now, if you think about it, contraction is essentially you take the two adjacency list of two vertices and you have to merge them, right? And the thing that you have to do, you have to, of course, delete delete the two lists, create a new list. This list is a merge list. Now, of course, there's going to be a big problem, right? Because think about a situation like that. It might be like that. Right. And now I contract this blue edge, right? So this is U, this is V, let's call it Z. After the contraction, this is going to look something like that, right? Chicken fit on both sides, but the edge, this is UV. This new vertex is UV, right? But now we have this edge with Z, but it corresponds to two edges, right? We had two edges collapsing in it. And we don't want to keep on maintaining two lists. So we are going to, in fact, for every edge, maintain multiplicity. So this is just going to say this edge has multiplicity 2, which means that corresponds to two edges in the original graph. Okay? Okay. So essentially what you have to do is, again, to contract an edge, you have to take the two adjacency lists, merge them, and if you have repeated edges in the adjacency list, you keep only one copy, but you added up the multiplicities, and that's it, right? And to do it efficiently, you have to kind of really look carefully on the presentation of the representation on the graph with adjacency list, and getting this linear time so that you can do the operation again and again and again. The details are not easy. They're not difficult, but they're very tedious, and you have to be very careful. You need to have cross pointers and stuff, and you're not going to be happy. One way to get around it is to use hashing, which is in fact what, if you look on all the implementation of graph algorithms in real libraries, that's what they do. They don't bother with all this pain. If you do that, then everything becomes much easier, okay? But if you're more interested in the details, they're in the class notes. But from this point on, I'm just going to take it on faith that you can do this. Contraction in O of n time, where n is the number of vertices. Okay. So that's nice. Why am I telling you that? Okay. So, Okay, so what happened if I take a graph, right, and I contract an edge, right? If I contract an edge in a graph, I'm getting a new graph. I get a new graph which has one fewer vertices, right? The two vertices that were at the endpoint of this edge get replaced by a meta vertex, right, that corresponded to old vertices. So from n vertices, we went down to n-1 vertices. And I can continue in this fashion, right? I can take some other edge and shrink it. Let's say this might be UV, this would be XY, right? After the contraction of XY, this is G of V. After I contract XY, right? This would just be this and so on, right? And I can continue in this fashion, right? Now, what's really going on here as I continue, and of course I can contract also from a regular vertex into one of those meta vertices, right? So I can do this, and I can continue this game, contract until I have a graph which has only two vertices, right? Okay. What happened here, right? This vertex, you can think about it, its name is going to be a vertex where its name is going to be labeled, at least conceptually. When we implement the algorithm, we don't do this labeling, not explicitly. Its label is going to be all the vertices that collapse into this vertex, right? Essentially what happened, this vertex, right, if you think about it, this vertex is going to correspond to some collection of edges that we contracted. But the way we contracted the edges one after the other, the collection of edges that were contracted into the single vertex are going to be a tree, right? So one vertex corresponds to a tree. The other vertex corresponds to another tree, like that. And so this is really going to be, this is going to be this. This is going to be this vertex, right? And let me use maybe colors. And this red edge might have multiplicity k. This would really correspond to k edges in the real graph going between those two trees. Right, maybe like that. Okay. So contracting the edges, contracting a sequence of edges until we remain with a graph with this, only two vertices really corresponds to computing a cut in the graph, right? Okay, so that's nice. Now I should say, by the way, I didn't mention it, but when we do the contraction, it's not a critical detail, but still, let me mention it. When we do a contraction, we can get this blue loop. We don't keep the blue loop. So whenever we get the loop, we throw it away. We don't care about self loops. They are not relevant for our purposes. Okay, back to business. Okay, so by the way, if you think about it, this contraction business, this is really one way of thinking about how MST algorithm works, right? So what does Kruskal algorithm does? Kruskal algorithm may sort the edges by weights. We're computing MST, so maybe I should, this is a side. Kruskal is contraction algorithm. And this would matter later on. So what Kruskal does, Kruskal start with one way to think about Kruskal is that you sort the edges by weight and you start counting them one by one. And when you take an edge in Kruskal, and if the edge is across two different trees, you merge the trees, right? You add the edge to the MST that you're building. You can interpret it in our language as contracting this edge, right? So one can interpret Kruskal algorithm as an algorithm that performs a sequence of contraction until you remain with a single vertex. And the tree of contraction you performed is the MST. Okay. This is a side comment. Why it relevant and important will become hopefully clear shortly later on. Okay, back to our business. So let's assume that we have an oracle. The oracle tells us which edge to contract. Okay, and in particular, oracle always return okay. So let's assume that we have an oracle that always give us an edge that is not in the min cut, right? So so let's see what happens, right? If we have this min cuts, right? We have this min cut. We have this set of blue edges in this min cut. By the way, there might be a lot of min cuts that are different, but we kind of fix the min cut that we want to argue about. And the oracle always provides us with an edge that is not in the min cut. It's either in the left side or the right side, and we keep contracting those edges, right? Then if this happens in the end of the game, okay, we will remain with exactly the min cut, right? We will have two vertices, those two meta vertices with a single edge, and this single edge would correspond to the edges of the min cut, right? So this gives us an algorithm to compute the min cut, right? Ask for the oracle to give us edges not in the min cut, contract them, repeatedly do this, and in the end of the process, we're going to remain with a single edge. The multiplicity of this edge would be the min cut, and we are done, right? Now, this is, of course, a loopy-loop logic, because how would the oracle know what is not, what edge is not in the min cut if it doesn't know the min cut, right? This is kind of faulty logic, but if we can do that, then we will have an algorithm, right? Now, I should mention, by the way, that the logic lying behind all this stuff is the fact that when I take a graph and I contract an edge, right? So there is UV, I contracted it, right? This is G over UV. I contracted the edge, I got this graph. Now, the important thing to observe is that every cut in this graph corresponds to a cut in this graph, right? So every cut on the right corresponds to a cut on the left. Now, there are cuts on the left that doesn't appear on the right. Which kind of cuts don't appear on the right side? Which cut do I lose by the contraction? Right. Any cut that cuts UV cannot be realized on this side, right? So we are losing, so intuitively, or not intuitively exactly, the number of cuts is 2 to the n minus 2, right? Minus 2 because we don't allow all the vertices or no vertices. And we reduce the number of cuts here to 2n minus 1 minus 2, right? And what we lost are those cuts, right? But the important thing is that you have to kind of go carefully and check it. But when I look on a cut here, and I look on the value of the cut in this reduced graph, right? I look at this reduced graph, I look at the value of the cut, I look at the number of edges that it cuts, I go back to the original graph, it's going to have the same number of edges cutting it, right? So in some sense, we did something good, right? The contraction reduced the size of the graph, right? When we design an algorithm, we always shoot for an algorithm that decreases the size of the problem until it becomes small enough, till essentially then we can solve it, usually using brute force, right? So that's why this idea of contraction comes in, because it reduces the problem and the size of the problem. And if we are lucky, if we're contracting an edge that is not in the min cut, then it does it in a way that preserves the min cut, right? Right. So if we always contract an edge that's not in the min cut, then the min cut is preserved as we go down. All the cuts on the right side appear on the left side. If we don't contract the min cut, then the min cut is still there. So we did not change the min cut. The min cut on the left side and the right side is the same, right? And that's why this oracle, this idea of the oracle always giving us an edge not in the min cut works. Okay. So that's the plan of attack. Of course, the question is, how to get rid of the oracle. Okay, so if you know Greek mythology, you know that you don't want to ask the questions of the oracle, right? Because whenever you go ask the oracle questions, you definitely get an answer, and it's definitely not the answer you want, right? It's always the answer of something horrible, terrible, no good is going to happen to you. Thank you for coming. Please don't come again. So the first task is to get rid of the oracles. They're really not something you want to have, both in the Greek mythology and in algorithms. So any idea, how do I pick the edge to contract? And of course, I'm going to refer you to the name of this course as a hint. Anybody has any idea? Yes, so the idea is to just pick random edge. Okay, so you have to be very careful how to do it. Pick random edge. So that's what the algorithm is going to do. Algorithm, it gives G, while G not a single edge. Pick random edge. Contract it. Contract it and return cut defined by edge, right? So we randomly pick an edge, contract it, randomly pick an edge, contract it, until the graph has only a single edge. The single edge corresponds to a cut. You return it as a candidate to be min cut. And of course, this looks like a criminal algorithm that should have no reason whatsoever to succeed. So the big question is, what is the probability the algorithm returns a min cut? Right. And it turns out, and you have to remember the trivial answer to this question is, of course, something like 1 over. Is the screen not updating anymore? Oh, it's updating. Yeah, just a bit behind. If the answer is something like 1 over 2 to the n, then it's no good. the probability is so small that there is no hope, right? So we want to show that this probability is much better. It turns out to be something like 2n squared, or let's write 1/n squared. It's not exactly this, but good enough for our purposes here. So I'm going to show you the probability of success is this, and this is already very good because it says that the probability of success is 1/n squared. Now I use amplification, right? This is p, then I need to run it 1/p times to get success with constant probability. If I run it log n over p times, I will get high probability, right? Now, to remind you, a contraction takes off n time. We are doing it off n time, so this algorithm has running time n square, right? The probability is roughly n square, so I have to run it something like n squared times. So the running time of this algorithm is going to be something like n to the 4th log n. What does this mean? I'm running this top algorithm here, n square log n times. Every time I run it, it's going to return a cut. And not now, for every cut that it returns, we can check how many edges are there in this cut. And we repeatedly do it, right? So we get a large number of cuts. And the algorithm is just going to return the smallest cut computed in all those attempts, and that would be the mean cut return. And the claim would be that with high probability, and high probability here I mean probability of 1 minus 1/n to the of 1, so probability very close to 1, the minimum cut computed would be the minimum cut in the graph. Of course, there is a small probability of failure. This algorithm can fail, but that's okay. Okay, so what would be the plan of attack now? I have to prove to you that the algorithm succeeds. Before that, I need to go down the rabbit hole of some low-level technicality. So let me go into this low-level technicality, picking the random hedge. Okay, so picking it is not easy because we have to pick the edges according to their multiplicities. So here's what we are going to do. So in particular, if edge has multiplicity 7, and edge is a multiplicity 1, the edge with multiplicity 7 should have 7 times the probability of an edge that have multiplicity 1. Or, an edge with multiplicity 16 should have, a factor of 16, the probability to be picked. The reason is because when we say multiplicity edge with multiplicity 6, let's say, what we really mean is that this represents 6 real edges in the graph, and each one of them has equal probability. Okay, so how do we do that? So that's a good question. So what we're going to do for every vertex, we're going to maintain the total weights of all the edges adjacent to it, okay? And they're going to have n vertices, right? So we have n vertices. Every vertex is going to have different weight, W1, W2, all the way to Wn, okay? Picking a vertex according to the weight is very easy, right? Because we're essentially going to pick a random number in this interval and see where, in which interval the random number falls, and that would be the vertex that we pick. Once we pick the random vertex, we look on all the edges adjacent to it, and we're going to pick the edges according to the weight in this list. Again, this list is linear size, most n, so this can be done in O of n time. So in O of n time, we can pick a random edge according to multiplicity. The only thing that is now complicated is that when you do the contraction, you have to maintain the weight of the vertices, right? The total weight of the edges adjacent to them. It easily can be done by the contraction. It's low-level details. It's not interesting, but just remember that one needs to do this. Okay, it's a boring detail that if you go and implement the algorithm you care about. Okay, back to our business. So our business is to bound the probability that the picking random edge and contracting it indeed succeeds. Indeed, we are able to do all the contraction without hitting the min cut. So, so we need for that two lemmas. The first lemma says that if min cut of G is size K, then the number of edges in the graph is at least Kn over 2. And the proof is pretty easy. Look on the vertex of the graph. The degree of the vertex of every vertex in the graph has to be at least K. Why? What happens if the degree of a vertex is smaller than K? This is a question. What happens if the vertex has degree 7 and K is much bigger than 7?
The vertex itself can be taken as the min cut.
Yeah, the vertex itself can serve as a min cut against everybody else. So the degree of the vertex must be at least the value of the min cut. So every vertex has degree at least K. And now you just need to remember the following, that the number of edges in the graph is equal to the number of the total sum of the degrees of vertices in the graph, right? Divided by 2, right? Divided by 2 because we count every edge twice. Since each one of those numbers is larger than K, this is Kn over 2, right? So we prove the lemma. Okay, so now hopefully you see what's going on, right? We immediately get that. So let EI be the event. Pick an edge, not in the min cut, not pick an edge, not in the min cut, in the ith random construction, ith random contraction. Okay, so what is this? So this probability is in fact, it's not well defined, this event by itself, if you think about it. But what is defined is the following. And I would explain why. Right. So the problem is that if you hit the min cut, you contract an edge in the min cut, right? Then the cardinality of the min cut might have changed, right? The cardinality of the min cut remained the same only as long as you're not contracting an edge of the min cut. So the probability of EI is really makes sense only if you had not contracted any of those edges earlier, right? Okay, so this probability, let's think about it. How many vertices does the graph has, right? So we performed I-1 contraction, right? Every contraction reduces the size of the graph by 1. So the graph at this stage has n minus I minus 1 vertices, right? Okay. So that's the number of vertices it has. right? And the probability it hits the min cut, right? We assume that it didn't hit the min cut in the first I-1 iteration. So there are k edges that belong to the min cut. Let's call this edges of gi-1. This is the graph after I-1 contraction, right? Okay. So this is the probability that we hit the min cut, right? And we want the complement, right? The probability that we are not hitting it is. Okay. Now, by the lemma above, right, the number of edges of gi-1, right? Move. This number is at least kn minus I plus 1 divided by 2, right? Okay. So, right, because this is where we are using the conditional probability, right? This means if all the precondition holds, the min cut is still of size k. The number of edges is just the number of vertices at least times k. At least it might be much bigger. Okay. As such, if I replace E here by something smaller, right? If I replace something smaller, make it bigger, right? So I get the lower bound of this probability. So this is 1 minus k. Oops. Let me write it in a different color because things are colliding. Okay. So this is this probability, right? Okay. But we are not really interested in this probability. What are we interested in? We are interested in the probability of E1, E2, all the way to probably En minus 2. Yes, right? So this is the probability that maybe E1. Yeah, E1. This is what is the probability I wrote? This is the event that all the contraction did not hit the minimum cut, namely the single edge we get in the end of those contraction is the min cut. So that's the probability we want to bound. This can be written as the product. I go from 1 to n minus 2 of probability of EI Okay, so this formula can prove directly quite in straightforward fashion, but don't think about it as such thing. Just think about it in the natural way, right? The natural way is that first we test E1, then we test E2, then we test E3, and so on, right? And only if we succeed in each one of those iterations, we will have success that all those events happen, right? That we did not contract any of these edges. So this is the intuition why behind this formula. If you want, you can prove it explicitly. So this is what? This is larger equal. Now I'm going to replace each one of the probability by what I proved. 1 minus 2 over n, 1 minus 2 over n minus 1, la, 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 right? Let me not write the end of this thing. In fact, let me write it now that I think about it. 1 minus 2 over 3. This is the last term, I believe. Okay, so we have this, right? Now, a question, of course, this expression looks frightening, okay? And as I said in previous lectures, the most important thing is not to panic. So let's not panic. So this can be written as follows: n minus 2 over n, right? This is n minus 3, right? Over n minus 1. n minus 4 over n minus 2, n minus 5 over n minus 3, and so it goes, right? All the way to 3 over 4 and 2 over 3. Okay. Now, you know, in the modern world, this is a big problem. We have cancel culture. So things cancel. This canceled with this. This canceled with this. This cancels with whatever is here, and so on, right? And in the end of this massacre, right? Oh, I wrote. Okay. The end of this massacre, yes. Oh, I think the last one is 1 over 2, by the way. Okay. So yeah, 1 minus 1 over half. Does this make sense? Just a second. Okay. Let me fix this. This is 2 over 4, and this is 1 over 3. Yeah. Okay, my bad. Okay, in the end of this cancel culture, what remains is n minus 1, right? And 2 times 1, which is 2 over n times n minus 1. And that's the end of the proof. So this algorithm succeeds with this probability at least, right? The probability of success might be higher if there are more min cuts, right? This is the probability of survival of a specific min cut, but there might be a lot of other min cuts. So the algorithm might kill some min cuts, but some other min cuts might survive. So this is a pessimistic estimate, but in the worst case, of course, it's tight. So as I just explained, this immediately leads to this n to the 4th log n algorithm, right? You just run this algorithm n square log n time, and the probability of failure that in all those runs you fail, all those runs fail to output the min cut is going to be this thing, right? Let's call this m. Right, and this using standard calculations, right? This is going to be smaller than 1 over n to the polynomial, which implies the running time that I claimed, so the n fourth, I meant n squared, which lead immediately to n to the 4th log n. Okay. So this running time is not great. Okay. This running time is not great. It's kind of bad. The algorithm is beautiful and simple and elegant. No, the algorithm stops when we have 2 vertices. That's very important. We are not stopping. Sorry, this is I'm replying to a question in the chat. The algorithm stops when there are 2 vertices, and the cut is between those 2 vertices there is an edge with multiplicity, and this edge corresponds to the cut in the original graph. Okay, and you have to go to the detail of the algorithm, but it's easy to verify that you can recover the original cut by slightly more careful bookkeeping of what collapsed into what. Okay, so the running time of this algorithm is not great, but it's polynomial and the algorithm is extremely simple, much simpler than using network flow and similar nonsense. Okay, how do we do better? So since I don't have a lot of time, I'm going to have to change into the speed of light. So, but here's the basic algorithm. The basic idea is to look on what happened, on the contraction process. Right? So the contraction process, the probability of failure, right? The probability that, or if you want, the probability of success was pretty good, right? It was this probability here, right? It was n minus 2 over n. Right? In the first iteration, we had a very good probability of succeeding and not killing the min cut. Then in the next step, it was n minus 3 over n minus 1. The probability was still good, right? It was still good, but it was not as good, right? It deteriorated a bit, right? And then what happened is that in the end of this process, the probabilities were appalling, right? There were 3, 4, right? In the last step, right? In the last step, the probability of failure was of success was only a third. Before that, the step before it was half, right? So what happened is that the probability of success of every iteration, it starts with very high probability of success in every iteration, and as we succeed, the probability of success declines, right? Fortunately for us, when we multiply those probabilities, we still get something good, but the end of this distribution, the end of this product is terrible, right? So the natural idea is to say, okay, let's stop at some point. Right. So, and we are going to stop when the graph has t plus 2, where the graph has t vertices, right? So I'm going to take the graph, t is going to be a parameter. I'm going to collapse the edges, do contraction under contraction until the graph has t vertices. So this is equal to something like t times t plus 1 divided by n times n minus 1. This is just the same thing, same calculation I did before, but I stopped it earlier, right? And in particular, this is half if I pick t to be something like square root n over 2, I guess. Over 2, or not as n over square root of 2, I think. N over square root of n over 2. Okay, no. Yes, no, yes, no, no, absolutely not. Sorry, n over square root of 2. Yes. So if I take this, then the probability is half, right? What it means that if I pick this t, I'm contracting the graph into half size, and the probability of successful contraction is half. Okay, so here is the fast cut algorithm. I might have to steal a minute of your time. I'm sorry. I'm going to create 2 copies, G1 and G2 of G. Copies. And then I'm going to, H1 would be contract G1 to T, and I'm going to contract the 2 copies into size T, and I'm going to return min cut, min of fast cut of H1 and fast cut of H2. Okay. And okay, so what's happening? I'm doing 2 copies of the graph. I do 2 independent contraction until this size T of this n over square root of 2. And now I call recursively on those 2 copies. Right. So this is the algorithm. The probability of this succeeding is half. The probability of this succeeding is half, right? Succeeding means that we did not contract the min cut, right? This algorithm would return the min cut if in the recursion tree, there is a path from the root in the recursion tree all the way to the leaf where all the contractions are successful. So think about taking the recursion tree, which is just going to be a binary, complete binary tree, coloring the edges by black, red and blue. Red is, let's say, success. Probability of red is half, and you're asking for a path that is completely red. Well, I already argued this was the coloring stuff we did before. I already argued that the probability of success of having such a path is h plus 1, where h is the height, which is roughly log fn, right? Log square root 2 of n, right? So this algorithm, the recursive algorithm I described, find the mean cut with probability 1 over log n. The running time deteriorates a bit. It's n square, I think, over log n, right? And so you need to do amplification again. You run it log square time, and you get an algorithm that with high probability return the mean cut, and its running time is n log square n, and returns the mean cut with high probability. So that's how the coloring game, this is why I did all this nonsense about coloring of the tree. And that's it.